Running Urban. Am I audible? Can anyone respond? You look younger now. Good evening, sir. Okay, thank you. So let us start. Let us start our week six discussion. So before that, I have few announcements. Uh, I request everyone to write your name in chat box so I can count your attendance as it is being asked by the NPTEL authorities, and I can keep track of that. So since people are joining and leaving at different times, so it's better if you can write your name in chat. So let us start our NPTEL live session of week six for the course of non-conventional energy resources. The course code is given here. It is taken by the Professor Prathap Haridoss from IIT Madras, and I will be taking your live sessions. So these live sessions are being held every week on Tuesday, 7 to 9 p.m., as well as these are available online on YouTube. And these slides are available at the Google Drive, and links are provided to you. So let us start the today's session. So for today's session, I have changed few plans. So we will start with the our assignments first because it is taking time to go through uh, all these slides and notes. So it will, if we start with our assignments first, we will have enough time to interact at the end. So as my introduction, I am Lalit Bharti. I am a PMRF fellow in the Department of Physics at IIT Kharagpur, and I am taking the NPTEL live sessions for this course. These are my email IDs and my LinkedIn profile. So if you like to contact me or connect me on LinkedIn, you're always welcome. These are our week six content. So some part of PN junction we already covered in last week. So we will take few PN junction questions, then solar cell band based on the junction, their characteristics and their uses. Then we will see the solar cell construction as well as at the end we will see some quiz problem for the last week. So I'm just starting with the assignments directly because all I have already explained the questions in the assignment in the solution. So it is well understandable here. So our first question is the Schottky causal limit suggests that the single solar cell has an efficiency that can reach 100% when the sun is overhead. So for that, you need to understand what is the Schottky causal limit. So this is basically the efficiency limit of a solar cell, or you can say a single PN junction solar cell for a. So this is the efficiency limit which to collect power from cell where the only loss mechanism is radiative recombination. So in simple form, this limit tells the maximum efficiency of a single cell which can be possible. So it is not possible to 100% efficiently convert the solar energy to electric or the in the electric energy. So let's say this is your sun, this is your solar cell. So there is always some energy loss. So even if you ignore the radiative and recombination losses, still you have a limit. So this limit is 33.7. So you cannot go for a single PN junction solar cell beyond this limit. So the condition is single PN junction. So we will see some kind of solar cells which are not single PN junctions. So what we have multiple layers or multiple PN junctions. So that enhance the efficiency of a solar cell. So that is not the case here. We are defining for a single PN junction. So this Schottky quasar efficiency, it is the limit for a single cell junction. So since only a fraction of photons are converted into electricity, so it cannot be 100%. So you always have some efficiency losses. So this limit is called the Schottky quasar limit. So it is 33.7. So the statement is false that you cannot reach the efficiencies of 100% wherever the sun is overhead or just directly in line with the solar cell, but you cannot get the 100%. So this is also because this plot shows band gap versus percentage of incident light energy. So these are the for the band gap only this black colored area is usable electric power. Others this blue says the green says the relaxation of band edges as well as the below band gap photons because the below band gap photons will not be absorbed by the system for the band junction in few other losses. So only this much part. So this comes around at the band. It is highest at the point of around 1.5, 1.5 or below 1.45 volt electron volt, and the highest value is 33.7. This is an important phenomena in case of solar cells. Then we come at the maximum power point of the solar cell. So what is a maximum power point? So power, if you multiply current with the voltage, you get the power. Power is usually in watts, current is in ampere, milliampere, and voltage is in volts. So this is a typical characteristic curve of a solar cell. So at the x-axis, we have the voltage, and at the y-axis, we have the current. So you need to understand first what is VOC and ISC. So VOC is basically the open circuit voltage. OC means the open circuit. So in the case of where you do not attach a load, or you can say that net current flow is zero. So this is your current, and when you get current flow is zero, when you get your current point as zero, you add the voltage, you will get VOC. So the open circuit voltage VOC is the maximum voltage from a solar cell and occurs when the net current through the device is zero. So this is condition of open circuit. So if you have a circuit, simple circuit, if you consider, if your circuit is broke or not connected completely, in that case, your highest voltage will be VOC. And your ISC is the short circuit current. Short circuit means you are just completing the circuit, but you have no resistance ideally. So your voltage is zero and your current is highest. So if you have the short circuit condition, your current is called short circuit. So IAC is the highest level of current and VOC is the highest level of voltage. So if you make this curve, this is a typical curve. If your voltage is decreasing, your ISC is increasing. Similarly, your IS is decreasing, your VOC is increasing. So you will get a point where the I times V that is highest. Because if you go at the right side, your current will drop, and if you go left side, your voltage will drop. So this is a point where the power is maximum. So the multiplication or the product of I and V is maximum. That is called the maximum power point. So this is the maximum power point. Similarly, for this cell, this kind of curve is obtained, and your maximum power point is here. So in this case also, you are showing the same thing. So the questions asked the maximum power point of a solar cell occurs at the open circuit voltage. So that is wrong because the open circuit voltage condition is here at VOC, but the maximum power point is the at this position where your I and V product is highest or the maximum. So this statement is false. So we understood the VOC and ISC and maximum power point by this question. So this is again the same question based on the maximum power point. So the question says the maximum power point of a solar cell may vary from manufacturer to manufacturer. So that is yes, that is true. Depending on the manufacturer, depending on the material, depending on the system type of the solar cell, your maximum power point can be different. So here we see that it depends on the material, manufacturer, technology, or etc. So if you go at the different temperature, your VOC will be your maximum power point will be different. In this case, your maximum power point is different. So it depends and it can vary. Yes, true. Then we have the fourth question. The question says during reverse bias, the N side of PN junction alone is affected by the applied voltage, applied potential. So during a reverse bias, so we need to reverse biasing it. P type will be at the negative and N type will be at the positive terminal. Only the N side of the PN junction. So this is the PN junction. Only the N side will be affected. So that is not true. We also, I guess, we discussed in the last class. So if you reverse bias it, your P side, N side, both side will be affected, and you will get a junction voltage. You will get a barrier here, and you will get a junction voltage, which will be distributed at both sides. Only there will be opposite charges at opposite sides. But you cannot say that only your N side will be affected or only your P side will be affected. So both sides will be affected equally. Your charge region may be different, and your depletion layer size or layer distance will be different, but your P side will also be affected. This statement is false. Then we go to our fifth question. It says charge density as a function of position is constant across PN junctions. So I guess this question also this type of question we also see in the last class. So it says the position of the function of position charge density. So this is your PN junction, and you can understand the different type of distribution. This is the distribution of charge. This is distribution of electric field. This is distribution of voltage. So at the N side, we have the positive charge at the junction, not at the N side. This region is the space charge region. So we will have the positive space charge region here, and being different depletion layer with your space charge region for the positive side is slightly higher than the negative charge region. And electric field, if you see, electric field curve is something like this, which will be highest at the center. Then as you go away from the center, your electric field will be different. And your voltage will be highest at the edges. And as you go at the center of the interface, your voltage will come around zero. So this statement is false, that your charge density is not charge density as a function of position is constant. So it is not constant. Then let us see the next question. So this question is on the Fermi energy level. So we already talked about what is Fermi energy level, how it is changing, why the bands are bending due to different Fermi energy levels of different material. So now we see the question. Question says both Fermi energy and band structures are flat when transferring across the across a semiconductor PN junction. So we know at the interface what happens. This is your intrinsic semiconductor. This is your N-type semiconductor. This is your P-type semiconductor. So for N-type, your Fermi energy levels are near the conduction band. For your P-type, your Fermi energy level are near the valence band. So as we put them together at the interface, your Fermi energy levels will align. Similar to, as I explained you earlier also, similar to two buckets of filled with water with different water level. As you connect them, your water level will get at the same level. Similarly, your Fermi energy levels shows your occupied level of your electrons. So as you put them together, your electron levels will go into the alignment, and your Fermi energy levels will align. Fermi energy levels, then this alignment will give you the band bending. So you can see the band bending here. This is your N side, this is the P side, and you see the band bending here. So there will be diffusion of holes, then will diffusion of electrons due to this band bending. And this phenomena is very much important for the solar cell. That is why you will get an electric field in this case. So it says that both the Fermi energy and band structures are flat. So that is not correct, because we know their band bending occurs at the interface in a PN junction. That is why we get this kind of phenomena. So this statement is also not correct. It is false. So let us go to the next question. So I guess we are moving quite fast this time, but let us see how much time we get at the end. So the question says, what is the advantages of amorphous silicon over the single and polycrystalline sample? So let us see. So we have already seen what is amorphous, what is uh, single crystalline, what is polycrystalline. So simply for the amorphous, your your crystalline size is not very well defined, or your crystalline size is very small, or you can see that there's no long range ordering in case of amorphous. For a single crystalline, you have very well defined single crystals, which are very long range ordering. So if you go from point A to point B anywhere in the crystal or in the lattice, you will see similar kind of environment, or you will see similar kind of crystal structure everywhere in your whole lattice. And polycrystalline is somewhere between single and amorphous, single crystalline and amorphous. So you will see some short range ordering of crystalline structures, but as you go slightly far from your crystal, so you will see that there are some different type of ordering. So it is called the polycrystalline. So this is some structure, this is some structure. So multiple phases are present in case of polycrystalline structure. So you can simply understand why the single crystallines are very expensive, and due to this kind of purity, because you need very pure phases in case of single crystalline material. So the quality is very high, the purity is very high, as well as the prices are very high. So we have already seen how the single crystalline silicon are obtained from the amorphous silicon, uh, different methods, float zone methods, and different other methods. So let's see what statement they're asking. It is more flexible to keep on a substrate or contour. So these are we are being asked about the advantages of amorphous silicon. So yes, these are more flexible. So if you see these are the amorphous silicon, and these are single crystalline silicon. So amorphous are more flexible, so you can put out any substrate rather than at single crystalline. Because if you see the single crystalline silicon discs, they are very rigid. If you have seen in lab or somewhere, they are very hard and brittle. So these are not flexible. Amorphous are flexible, but single crystalline are not flexible. Second statement, it possesses more dangling bonds, as does the more number of defects. So yes, they have more dangling bonds because the impurity is not higher. So, but this is not advantages of say amorphous silicon. So we will not take this statement as correct because these dangling bonds are not we are not taking as them as advantages. The third statement is it is more effective in capturing solar radiation. So no, if single crystallines are more effective in capturing the solar radiations and the efficiencies are higher for single crystalline as we have discussed earlier, but due to our cost effectiveness we are using the amorphous. So it is the first statement, it is less expensive. So yes, the amorphous are less expensive due to their less purity. So these four statements, the first statement is correct. So there's one doubt when you see a single crystalline solar cell and single crystalline, amorphous solar cell, you can see the amorphous solar cells are square in nature to fill the whole space of a solar cell. But your single crystalline solar cells are in this shape. So they are cut at the corners. So this is called the diamond shape cutting. So can anyone suggest why you see this kind of structure? And if anyone like to make a comment on this, why only the single crystalline solar cells are in this shape, and you can easily distinguish between single and amorphous solar cells by this cutout at the corner. Would anyone like to make any comment on this?
Like regarding 110 1 1 like some symbols for recognizing the for the P type, N type, and cut during lecture.
That is correct for identifying the silicon wafers at the lab. But if you putting it on on a solar cell, let's say your solar panel at a rooftop, then you don't need to understand what is P type, which is N type. And this is not your single solar cell. You're not your P type or N type substrate. This is a complete solar cell. This is your complete solar cell. So it is already having some, let's say, some sandwich structure, and you don't need to understand. Don't need to know what is there at your rooftop because you are looking at it, but nobody is caring about what is there at the solar panel. So your statement is correct that it is being identified by that cutout, but here the reason is something else. So the reason is the reason behind this structure is their manufacturing process. So as you saw, how your single crystalline system was grown. So I don't know. Yeah, this kind of. So we already saw that your different type of manufacturing processes were used. So either float zone process or different processes were used. So in both cases, you will get a circular crystalline, your circular disk of either silicon of p-type doped or n-type doped, but you will get a disk kind of structure. So that is why you are always having the pure single crystalline silicon in form of disks, in form of circular disks. So you need to cut them to fit the solar panel and to minimize this space, to minimize the wastage of the space. These are being cut in like that. So initially it was circular like this, but you had to fit it because if you put in circular way, So your most of your space will be unutilized. And for a solar cell, solar panel, what you need the whole area to be covered by the solar cell. So in case of amorphous, you can easily get in any form, because we saw that amorphous silicon we had a liquid of that, and we can pour the liquid and we can make any random structure. But in case of single crystalline, we have the circular discs only. So in industries, most of the the silicon or the single crystalline pure silicon is available in form of circular disc. That is why we need to cut it, and to minimize the wastage of the space, we already put it together. We always cut this shape in this shape at the edges, and we put it together to at the solar panel. It is
Sir,
also a
finally, yeah.
yes, yes, yes,
Sir, means we cut in this shape to cover the maximum area in the solar panel, right?
yes, yes.
Okay, sir. Thank you.
Bec- Because for amorphous, we can make it in any form. So you can directly make it in a in a square or in a rectangular form, but it is not possible for single crystalline, because you always have in form of disc. So you need to cut it to maximize the surface area and utilize the maximum portion of your solar panel. So next time, if you see this kind of cutouts, so that is clearly a single crystalline solar cell. So it will be costing you higher, because the purity is higher, your efficiency will be higher, but the prices will also be higher. And if you have this kind of structure, it will be either amorphous type, or we have many more different types of flexible and different type of solar cells, which will we see in our future classes. Okay, so let us move to our next question. It says the solar cell components and ideal resistance of that. So we have new solar cell. So we basically have two types of resistors. So one is shunt resistor and second is series resistor. So if you see, this is you can say the model of electrical model of a solar cell. So this is your PN junction, and this is your current, the direction of current flowing, or this is your solar cell. So basically, this PN junction is representing your solar cell. So there is one series resistance, there is one shunt resistance. So your one resistance should be very high and one resistance should be very low. So your current and this is your load. So voltage is being measured at this point between these 2 points, and this is your L is your load. So your most of the current. So let's say this whole portion is your solar cell with the current and your PN junction. So current is flowing in this direction. So your whole current should pass through your load. Okay. So this is your IL, the load current. So whole current should pass here. So your series resistance should be very low, very low. So RS should be very low. So it is simple that if your resistance is low, your losses will be low and your current flowing will be higher. And your shunt resistance should be very high, that no current is flowing in this direction. So because if your current is directly flowing in this direction, like this, in this circular pattern, you will not get the current at this edge or at this load. So what you need your load to be maximum, you need load to get the maximum current. So your series resistance should be very low and your shunt resistance should be very high. So shunt resistance is also representing your losses or your resistive losses of a solar cell. So if your resistance losses should be very low, but so your RSH should be high and RS for your series should be low. So what happens for your new solar cell? Your condition is, yes, you have the high shunt resistance and low series resistance. But by the time your resistance changes and your you can see in your old solar cell, your shunt resistors get lower and your series resistance got higher. So it is representing that your resistive losses are increasing by time. So there are various phenomena why the shunt resistance or the resistive losses are increasing by the time. So you see your new solar cell, by the time the efficiency will decrease. So if you like to mark it, your shunt resistance should be very high, or A should be 1 for new solar cell, and your series resistance B should be low. But for a edge solar cell or your old solar cell, it will inverse, or your solar shunt resistance C will get low and your series resistance will be high. So you need to understand this concept. This is the most simple model of the solar cell, and how your series resistance and shunt resistance are important in case of solar cell. So this was done. Next question is, this is a fill factor. Fill factor is very important for any solar cell. So what is a fill factor? Fill factor is basically your ratio of maximum Pmax versus Pt. So let's come with that, but uh, let's take the definition. Fill factor is the ratio of actual maximum obtainable power, or Pmax, to the product of short circuit current and ISC and the open circuit voltage VOC. So we know that P maximum power point, the Pmax or the PMP, the maximum power point, which that will be the highest for that. But what is the maximum obtainable power? Obtainable power means what we can really get. So one is the highest ideally, and what we can actually get. So the ratio of that will be the fill factor. So the fill factor will define your power conversion efficiency. So how much power consumption, power conversion efficiency. So if your fill factor is higher, your efficiency or the efficiency of a solar cell will be higher. So this is always less than 1. So here you see Pmax is P maximum power point and V maximum power point. So this is a Pmax, and divided by VOC and ISC. So we know that VOC is highest point and of voltage, and ISC is the highest point for the current. So this is your PT. This is your multiplication of, or the product of, VOC and ISC, and this is a maximum power point. So this was a maximum power point. If you take the value of the voltage here, so that will be called VMP, and total value of current here, it is called IMP. So that is your Pmax, and this is your PT. So the ratio, which is IMP times VMP divided by ISC times VOC. So that is a fill factor. So both are option 2 and option 4 are correct. Just they are taken this in inverse. So these options are correct. So fill factor is quite a interesting phenomena and important phenomena for a solar cell. Let us take the next question. This was the fill factor. The next question is again on the this model of your solar cell. So we have the different symbols, and we need to match to the components. So your A is, we already discussed, this is your current source. It acts as your current source or a photo current. So photo current means photo generated current. So this is your A is your photo current. B is your, we know that the current should not flow here. So it should be very high. So it is called the shunt resistance. So B is your shunt resistor due to the internal recombination of electron hole pairs. So it is representing, the shunt resistor is representing your internal recombination or the losses due to the recombination of electron hole pairs. C is your C is your series resistor due to the contact resistance. So it should be very low. So the contact between different layers and the external contact context, these should be very low in resistance. So these are series resistance, and D is basically your load. So D is your load resistor. Where A will go to 4, B will go to 1, C will go to third, C is third, and D is 2. So these options are this solution is correct. So this is again the same model we talked earlier in the previous to last question. So this is also done. Then we come to our question number 6. And question number 6 says the open circuit voltage of a solar cell, or the VOC. So it varies with the exponential photocurrent. So this is your VOC. This it varies with your exponential of your photocurrent. So that is not correct. Okay, let me uh, just first repeat all the statements. Does not vary with temperature, varies linearly with temperature, varies with logarithmic of the photocurrent. So to understand the relation of VOC with current, you need to take the solar cell equation. So this is basically a solar cell current equation. So I cell is equal to I naught minus I pH. pH means this is your dark current. I naught is your dark current. pH is your photocurrent. And E times QV divided by KT minus 1. So this is basically your simple solar cell current equation. So for open circuit voltage, if you just convert it, your VOC will be something like that. And you for case of short circuit voltage, your ISC or I or J is same here. So your ISC will be minus IPH for the photocurrent. So this 2 3 condition you need to be taken to keep it in mind, that what will happen in case of short circuit and what will happen in case of open circuit voltage. So clearly your open circuit voltage is directly related to your temperature. So if you increase your temperature, your photocurrent, your VOC will increase. We already saw this kind of relation in your previous some question here. So your VOC, this is your VOC. So as you increase your temperature, your VOC is increasing. So you see here for 70, for it should be higher actually. So for your different temperatures, your VOC increasing. And whereas, yes, so VOC is increasing. Similarly, it should increase with the photocurrent. So it is IPH or JPH. So this is the photocurrent. So there is a logarithmic relation here. So the statement says it varies with logarithmic of the photocurrent. So that is correct. That you have the ln here and the photocurrent is here. So VOC depends on the temperature, directly proportional. VOC directly proportional to the logarithmic of your I photocurrent or the IPH. So statement third and fourth are correct. Second is incorrect because it says it does not vary with temperature, but we saw that it varies with temperature. And it varies with exponential of photocurrent. So it is not correct because it does not related with this exponential relation. It is related by the logarithmic relation. So these statements are clear with this cell equation or solar cell. So you should keep these three or these equation in mind. It is already been taught in the main lectures, I guess. So in detail, you should know each and every element. And in case of open circuit voltage, as well as in case of the short circuit voltage, short circuit current. So the option third and fourth are correct here. Okay. Let us go to the next question. So we already talked about the direct band gap semiconductors, indirect band gap semiconductors. What is the advantages? Why most of the metals for solar cell are made up of particular band gap semiconductor? So let us take this question again. So bulk lead sulfide material can absorb the full visible spectrum because bulk lead sulfide material can absorb the full visual spectrum because it is a direct band gap semiconductor or it is indirect band gap semiconductor. So the statements are not correct because we know that for absorbing the solar of the observing the spectrum or the visible spectrum or any spectrum, what is the condition? The condition should be your EG or your band gap should be either equivalent or slightly higher than the incident solar energy or the spectrum energy. So if you have this, be it be direct band gap semiconductor, be it be indirect band gap semiconductor, it will be absorbed. So it doesn't depend on the type of semiconductor. It depends on the what is the incident energy of a radiation and what is the exact band gap of the particular material. So that is why these two options are correct. Third is the bulk lead sulfide band gap lies in the middle of region with respect to wavelength. The bulk lead sulfide band gap lies in the middle of the region with respect to wavelength. And the first statement is bulk lead sulfide band gap correspond to lower wavelength than that corresponding to the region. So for that we need to understand we need to know that what is the band gap of bulk lead sulfide material. But if it can absorb, but we don't know the exact values, but they are showing that it is already absorbing all the full spectrum. So we know if your energy is Eg is higher than E or your band gap is higher than your incident energy, then only it can be absorbed. So if you convert your energy to wavelength, then your wavelength should be lower for the corresponding. Uh, your band gap wavelength should be lower for the corresponding radiations. So this is correct. The the bulk lead sulfide band gap of the material band gap to the longer wavelength than the corresponding to the region. So band gap should be lower or your energy band gap should be higher. Both cases. You just need to convert your energy to your wavelength. So the option fourth is correct only. So it is not related to the being middle of the region. Band gap should not be in the middle of the region. It should just be higher than the incident energy or the incident spectra. The option four is correct. Rest are incorrect.
Sir, one query, sir,
Yeah, sure.
regarding same question. Am I audible?
Yes, yes, yes.
Sir, during lecture, sir told lead sulfide material has a direct band energy, direct band gap semiconductor
Yes,
during lecture.
yes, yes. So it is direct band gap. Yes, then.
So first option is not correct.
But the statement is, yeah, it is direct band gap or indirect band gap. But the statement is why the lead sulfide metal can absorb the full visible spectrum. So being direct is no, it is not the reason of absorbing the spectrum. Yeah, that is correct that it is direct band gap semiconductor, but it is not the reason of the statement. So we are being particular about the statement given in the question. So if they ask which kind of semiconductor it is, we can say it is direct band gap, but it is not the reason. But because if same band gap material is in direct or in indirect band gap, it will again absorb the same wavelength of the full visual spectra. But this question is not related to the type of semiconductor. I'm just showing just to compare these, but it is not related to the direct band gap of or the indirect band gap of the material. So the accepted answer is given the question is given the option 4. So this question was already given by the professors or the question setters. So that is why I'm taking the fourth option correct only, because the statement is not clear here. The statement is not asking for the type of the material, and this statement, the statement first, that is not the answer to the question asked. Okay, you can just understand why we are not taking the option first as correct option.
Okay, sir.
Are you
Thank you.
getting my point?
Yes, sir. Yes, sir.
So next question is, so here we are showing the different type of solar cells. So the question is, space solar cell improve solar cell efficiency by using materials with blank band gap values. So we have amorphous silicon, tandem, tandem, amorphous, and tandem. So first we need to understand what is tandem solar cell. So basically, tandem means multiple layers of solar cell. So this is your solar cell one, and this is solar cell two. So why we are using different solar cell? We can use only a single channel solar cell or a single junction solar cell. But what happens when you have the sunlight at the solar cell? So different wavelengths have different depth of interaction for the different depth of penetration through the solar cell. So what will happen? Some let's say the higher wavelengths or the higher energies, they will interact more at the surface, near the surface, and it will absorb near the surface. And some will be absorbed, will not absorb and will go deep inside the solar cell. So if you use this kind of solar cell, let's say this condition one, so the higher wavelength, this higher energy will be utilized, but the lower energy wavelengths will not utilize because they will penetrate through and they will not be utilized here. And in this case, in the second type, only this region is utilized, but your higher energy wavelengths are not utilized. So what we can do, we can make a system, a hybrid system, which have one layer of this type of solar cell and one layer of this type of solar cell. So it will higher energy photons will be absorbed here, and the lower energy will penetrate through, and they will absorb here. So this is the example. So we have a TiO2 type perovskite solar cell. So the higher energy photons are absorbed here, and the lower energy will not absorb here, but they will penetrate through this junction, and they will be absorbed in the silicon region for this different type of solar cell. So we are just making the layers of solar cell which are active towards different type of spectra, different spectra of a visible or the solar spectrum. So by that, you will have very higher efficiency solar cells. So let's say the efficiency was high for the upper cell was higher for high energy photons, and the lower cell was higher for sorry, for high energy photons. The perovskite solar cell have higher efficiency, and for low energy photons, you have higher efficiency for silicon type of solar cell. So you make a sandwich kind of structure. So this is your PN1, this is a PN2, and you can have multiple of that. You can have 3, 4, and more, depending on the different type of material. But usually they are limited to 3 layers. So that is called the tandem structure. So the tandem is, sometimes they can get efficiencies more than this QS limit or quasi Schottky limit. That is why we are always saying that quasi short
So not audible, sir.
Uh, am I audible now?
Yes, sir. Now audible.
Okay, so I'm changing the microphone, so you may get some noise, but I should be audible at least. Okay. So where we were? So we are at this tandem type of solar cell. So the this different layer of solar cell, they are active towards different type of different energy levels of photons. Its meaning is their band gaps are different. So the top layer is the band gap of top layer this solar cell is tuned for the higher energy photons, and the band gap of this lower solar cell is tuned for the lower energy photons. So by that we can absorb all the from the higher energy to lower energy photon. So the efficiency will be much higher. So that is a good type of next generation semiconductor. Sorry, next generation solar cells. So that is clear now. So your option tandem and different. Your option two is correct. Yes, option two is correct. So now we see our 10th question. So it says, according to the SQ limit or the Schottky-Queisser limit to the single PN junction in blank AM 1.5 solar radiation with band gap of 1.3 watt electron volt, the efficiency is obtained. So then we again need to check the condition of the SQ limit. So SQ limit is basically for single PN junction as well as yeah. So first it is for the single PN junction. Second, it is for unconcentrated light. Unconcentrated means you can concentrate your light with solar. We already saw the different type of solar concentrators. So if you concentrate your light and you incident this light on a solar cell, then simply your efficiency will be higher for that case. So the SQ limit is defined on the unconcentrated AM 1.5 solar radiation. So AM 1.5, what is AM 1.5? So it is not covered in the assignments, but this is the condition for standard tests for solar cells, and you you might have seen in the main lectures what is AM 1.5, AM 1.0. So it is depending on the position of sun and different at different angles. So the SQ limit is defined on unconcentrated light AM 1.5, and they are asking for the band gap of 1.35 electron for what will be the percentage. So this is your Schottky limit, or this is your efficiency curve for different band gap. So you see at the 1.34 electron volt, this is highest. So the SQ limit is defined at 1.34 electron volt. So which will be highest will be 33.4. So this is your SQ limit. So the question is simple again, simple to understand. The SQ limit is for a single PN junction with unconcentrated light of AM 1.5 solar radiation, and which is 33.4 for the band gap of 1.34. Then again, okay, so we have now finished this part, and these questions are from the week 5. So these were in the your main questions, I guess, your main assignments, which are graded, and I have taken these questions from
Sir,
there.
question.
Yes,
Sir, question number 9. Please repeat. Question number 9.
9. So this question, this one.
Uh, sir, this is 10 number question. 9.
So okay, I get this one. Actually, this is 8. I think 9 is not there. So this is 8th question. So this you want to repeat it?
No, no, sir. This is 8 number question. 9 number question missing.
Yeah, I guess there is a problem in this slide. So 9 question is number is not there. So we are just have this 8 and this 10. Okay.
Sir, can you say further 1 to 7 because of I'm late.
1 to 7. You want it
Just
to get repeated?
yes, sir.
So what we can do, we can just have these 5 questions, and then I will repeat it for you quickly. Okay,
Okay.
so let me finish it first. Just 5 questions from last week, and then I will repeat.
Okay, sir.
So this question is again from the last week 5 discussion. So we have two extrinsic material with different band gaps, but each less than 2 electron volt. Means they are saying that these are semiconductors, are kept in contact with each other, are in equilibrium with each other. So it implies blank are same at the contact points. So what will be same at the contact point? Optical transparency, chemical potential, thermal conductivity, or the Fermi energy. So we know that if you put two semiconductors with different type of doping at the contact, your Fermi energy levels will align. So at the equilibrium with that each other, what will be same? So your Fermi energy level will same. So that is correct. Thermal conductivity have no role in this, so it will not be same. Optical transparency also do not have any role here because that depends on the respective band gaps. And chemical potential, because we already discussed in previous class that what is a chemical potential. So this Fermi energy is basically representing your chemical potential. So depending on the where your electrons are being filled, so these are basically the same phenomena and different aspects. So option 2 and option 4 are correct here. Then go to your question 2. So it says the statement is a set of 5 material out of which 2 are having overlapping band gap structure, while the remaining are having band gap between 4 to 5 electron volt, are kept in sunlight by the whole day and then taken back to the dark room. So what will happen? So we are marking 1, 2, 3, 4, 5 material here. So 2 are overlapping. So this is your conduction band, this is your valence band. So these 2 are overlapping, means they are conductors. And while the remaining are band gap more around 4 to 5 electron volts. So 4 to 5 means they are simply non-conductors, or you can say insulators, because if they have semiconductor, their band gap would be below 2 electron volts. So the conclusion we have two materials are opaque in the visible light. So the 2 means the first and second. So they are opaque to visible light. So we know that yes, conductors are not transparent to visible light. So we already discussed why the metals are shiny or the metals are non-transparent. So we see that why we already seen what is the reason behind that, why they are shiny and why they are not transmitting light. So these two conductors or these two metals will be opaque in the visible light. So A is correct. IR radiation will be emitted by material. So what we are doing, we are first putting it in sunlight for a whole day, and then we are taking into the dark room. So we will also discuss the black body thing, black body radiation, and whatever material you have, if you put in a higher temperature, so they will absorb this the spectrum. Oh, sorry, if you put in a sunlight, they will uh, absorb the spectrum. They will get heated or get the higher in temperature. And if you put in a dark, dark room or a lower temperature region, they will emit some light. So basically, they will emit the IR light. So it happens with each type of material, be it be semiconductor, be it be conductor, be it be uh, insulator. So these are the thermal properties basically. So B is also correct. C says material with band gap between 4 to 5 will transparent to visible light. So that is correct. Okay, if your band gap is higher and your EG is lower, then it will not be absorbed and they will directly transparent to the light. So that is correct. So we have the option A, B true, yes, B, C true, A not true, and C true. So option third, that is not correct. All remaining three are correct. So basically our conclusion A, B, C, all three are correct. Okay, so that is done. Then we have the question number 3. It asks that what is the material requirement for generating electricity from sun? So we have already discussed this kind of thing. So it should not be opaque to visible light. Should not be opaque to the visible light. Band gap lower than 3 electron volt. A material with electron holes as charge carriers. A material does not absorb infrared light. So we have already seen that it should not be the statement. It should not be opaque to visible light. So that is incorrect because for it the material requirement for generating electricity, they should be transparent or the band gap of EG should be higher for that 3 electron volt. So it should be higher. So they should not be opaque. They should be either absorbing or transferring, but they should not be opaque for that. So statement 1 is not correct. Your statement 2 is simply correct. Your band gap should be lower than 3 electron volt. Otherwise, they will be insulator and there will be no such phenomena of PN junction and all. So your solar cell will not be formed with this case with the band gap higher than 3 electron volt. So opaque, it should not be opaque. Then a material with electrons and holes, you should have the charge carriers. That is why the p and n side will be formed. So your different type of dopings will generate either electrons or holes in the semiconductor. So it should be there. And a material which does not absorb infrared light, so that is not correct. But the option second and third are correct. Then we have the fourth question. If electrical conductivity of a material is proportional to temperature, then its charge carrier concentration will also follow the same trend. So the electrical conductivity of a material is proportional to temperature. So electrical conductivity is proportional to temperature. Then the charge carrier concentration will also. So you can see this thing that your electrical conductivity is due to your charge carriers. So if you have, let's say, electrons as charge carriers or holes as charge carriers, your electrical conductivity is due to the charge carriers. So for the higher temperature, your charge carriers concentration will be higher. So that is also from, if you see any semiconductor or your any current equation or the charge carrier equation, for the higher temperature, the number of charge carrier will increase. So if your charge carrier increase, your electrical conductivity increase. So your temperature is also related to your electrical conductivity. So they both follow the same trend. So this statement is true. Then we have the fifth question. So it says which region of PN junction is critical to capture the capture of solar energy by preventing recombination. So which region? So we know that this only this middle region, which is called the depletion region or the space charge region, that is important for us. So this is critical to capture. All the P and N side, these are not critical or where recombinations happen. So only this region is critical to our PN or our solar cell applications. Okay, we have more questions. How many? Okay. So this is done. The sixth question is we need to just match the thing. Asymmetric space region, symmetric space region, symmetric diffusion length, and asymmetric diffusion length. So your space region and your space diffusion length depends on the doping. So if you have equal doping, you will get a symmetric space region. So your A will lead to second and B lead to first. Asymmetric to equal, asymmetric to unequal, and symmetric to equal. Similar for the CD case. So your all three options, the first, second, and fourth, these are correct. Then we are again at the band bending. So what is in this question? It says when two semiconductors brought in contact with each other and the Fermi energy of P and N region, the type region equalize such that EFP is equal to EFN. So EFP means your P type of Fermi energy level and EFN is N type Fermi energy level. So it results in what? So we know it results in band bending. So not band, flat band, not the entire material, not the asymmetric space. It is directly related to the band bending. So that is clear. Then we have question 8. This is all we have already discussed earlier. Okay, this is slightly different. In reverse bias condition, the internal electric field. So for a PN junction, the reverse. This is your this PN junction is in reverse bias. Your P type is connected to your negative terminal, and N type is positive terminal. So you have a barrier. So you have an electric field basically. So it opposes the flow of current. So if you have a flow of current, let's say from positive to negative. So this from positive to negative, there will be a barrier which will not allow your PN, your current to flow. That is why you get a for a PN junction characteristic diagram. You for the negative region, you get a very low current to pass until the junction is broken. So it opposes the flow of current. That is correct. Assist in flow of current. That is not correct. Incorrect. Does not have any impact and reverse the flow of current. So option second, third, fourth are not correct. Only option 1 is correct. Then we have the for the float zone process and Cholavsky process. We have already discussed what is float zone process and what is Cholavsky process. Direction of growth of single crystalline is opposite in the both two processes. Yes. So we saw that in Cholavsky process, this is your Cholavsky process. Your direction is upper side, and for the float zone, your RF coils are moving, so your direction is opposite in that case. Float zone process gives higher purity silicon. So yes, float zone. This is a float zone with moving RF coils. They are giving you more accurate or the more higher purity. Churasky process gives you larger crystalline size, so that is also correct, because in Churasky your whole silicon wafer, these are moving, so you are not restricted with the RF coils, so you can have larger size comparatively to the float zone technique. Then both use RF heating coil, but Churasky process coils are stationary, so correct. They both have the RF coils to heat the this area, but in your Choralski, they are stationary. So your whole this kind of tub, this containers is getting heated, where in the float zone your RF coils are moving. So that is why your uh, these are moving, not stationary, along with the growth of the silicon, single crystalline silicon. So these are higher purity as well as smaller in size compared to the Choralski process. So we have already discussed this. That's why I'm just keeping it quickly. Then we have in zone refining process, the sample solidifies first, blank, then the last. So this is your zone refining process. So this is for case of let's say germanium. So we have metal rods here, and we have coils here, induction coils. This is case of germanium. So this is a less pure region. This is a pure region. So what we are doing here, so it is similar to your float zone technique. So by using this heating coil, we are heating this area, and let's say you have a pure seed here. So we are aligning the amorphous germanium along with the seeds crystal structure, crystal, and we are making a pure type of germanium metal, or let's say semiconductor. So from we are moving from left to right, and as you are going, your heater is surpassing here, your material is getting pure. So we are going from pure to unpure. So in zone refining process, the sample solidify first is more pure than the last, or having less impurity. So this region is pure or having less impurity, and this right region is less pure or having higher impurities. So this is similar to your float zone technique. So okay, our discussion, our all questions for this week are done. So I am just okay, as requested, I am repeating your questions from 1 to 10. So I will just quickly go through. So let us take me a break of 5 minutes. Then I will just repeat it for you. And
Sure, sure.
meanwhile I request you to mark your attendance, as the attendance is required from the NPTEL site. So in chat box, you can just write your name, and I will just take count of the attendance for today.
Sure, sure.
क्लास खत्म हो गया सर?
No, we'll just taking a break. Okay, so let me start. So our assignment questions are done, but I am just repeating few questions as requested, and I will quickly go through these questions. And the detailed or the class is already recorded, and you can always see at the it on YouTube. So you can also go there, but I'm just repeating it quickly. So the question one was the both the Fermi energy and the band structures are flat when transferring across semiconductor PN junction. So we saw that yes, that is not uh, flat, because if you have any interface of P and N junction, and they will align, your band gaps will align, and you will get a band bending. So your bands will bend it. So the statement is false, that they are not flat. Then the question was on the comparison of amorphous, single crystalline and polycrystalline. So in last class we already saw what is single crystalline, which is having very long range ordering. Then amorphous, which is having uh, random kind of ordering, and polycrystalline is between both of them. So this is showing the amorphous, this is single crystalline. So our amorphous is more flexible, you can see here. So that is why the option one is correct. So it is having more flexible, and that is why it is advantageous. The second one is possesses more dangling bond and more number of defects. That is correct. That is possessing more dangling bonds or more impurities or more defects, but that is not advantageous to us. So that is why the statement is not true for us, because only we are taking the advantages of amorphous silicon. Then third one is it is more effective in capturing solar radiation. So that is incorrect, because we know that single crystalline or the pure phase is more efficient as well as more expensive.
ये वाला गेट खोल दिया है।
So the options first and option four are correct. So someone's mic is not mute, so you may mute your mic. Okay. So option one and option four are correct. Then we had this, we need to match the solar cell and the resistance. So this is the electrical model of a solar cell. So basically we have a photocurrent here, we have a PN junction here. So you have different type of resistance. So first is series resistance. So this is due to different contacts. So it should, and we have a shunt resistance. So this is representing the uh, defects in the solar cell or the resistive elements. So what we need to flow the current to this series resistance and towards this load. So we have the load here where the voltages are measured. So most of the current should be passed through this. So that is why your series resistance should be lower. It means your contact resistance should be lower, and your shunt resistance should be very higher. Means there should be no current passing in this loop. So it means the resistive losses should be very low. So your value of RSH or shunt resistance should be higher, and your series resistance value should be lower. But as your solar cell gets it, your solar cell efficiency get down by the time, your shunt resistance gets lower and your series resistance gets higher. Means your resistive elements are increasing and your series resistance are your resistance are your shunt resistance is decreasing, and it is which is representing your resistive your efficient or you can say your efficiency is losing by decreasing the shunt resistance. So for by the time your RSH values are getting lower and values are getting higher. So you can match it. Shunt resistance should be high, series resistance should be low, and in your old edged solar cell they are getting inverse. So this is the question is on your fill factor. Fill factor is basically your measure of your maximum obtainable power. So it is a ratio of P max. P max means maximum actual obtainable power with the product of ISC and VOC. So ISC, VOC we already discussed. So this is your VOC point, which is the highest open circuit voltage, and ISC means your short circuit current, which is the highest current point. So this is your PT. PT means VOC times ISC, and this is your maximum power point where you get the product highest. So if you align your maximum power point with the voltage, so we will get VMP and IMP. So the ratio of these two, that is called the fill factor, which is always less than 1. So more your fill factor, more efficient your solar cell is. So your option 2 and option 4 are correct, just a different representation. Then we have again the same. We just need to match the following. So your A is your photocurrent. So A, and this is your PN junction. So this part is representing your solar cell. So A is your photocurrent. B is your shunt resistance, C is your series resistance, and D is your load. So these two are interchangeable. That is why we are making these two current. So these are interchangeable or equal around equal in resistance, because they are already, you can see these are connected. So you can take CS series or DS load, or vice versa, DS series and CS load. Then we have the these four statements on the VOC. So we need to correlate VOC or the open circuit voltage with the temperature and the photocurrent. So this is the cell, the current equation for a solar cell. So I cell means the total current from the cell is equal to I naught, which is means direct current, minus IPH. So IPH is photocurrent, times E to the power QV by KT minus 1. So for the case of open circuit voltage, you get VOC is NKT by Q ln IPH or JPH by J naught plus 1. So your VOC is directly related to your temperature T. So that is correct. That is related to T, and VOC is directly proportional to the logarithm of IPH. Means your IPH is not directly related, but the logarithm of IPH is directly proportional to VOC. So these two statements are correct, and A and B is not correct because it is not exponentially related to the photocurrent, and option 2 says it is not varying with temperature, but it is varying. So that is why the third and fourth are correct. And for the short circuit current, you get ISC is equal to minus IPH. So this is the condition. There both conditions are from this current equation. So you should understand the current equation and different conditions of the current equation. Then we have the seventh question. Seventh question says the bulk lead sulfide material can absorb the full spectrum because these are semiconductor direct band gap semiconductor, indirect band gap semiconductors, but that is not related to us because being direct or indirect doesn't give you the reason of being visible spectrum or fully visible spectrum, absorbing the full visual spectrum or not. Although your lead sulfide is direct band gap, but we are not taking this statement as correct because it is not the reason of absorbing the full visible spectrum. So the reason is your EG is, or your band gap is lower, higher than the incident E. E is the energy from the solar, this full visible spectrum, or the wavelength is lower. So if you convert your E to lambda, so your wavelength will be shorter than the incident wavelength. So the option fourth is correct here. Then we have the fourth one, the eighth one. So eighth is due to the tandem solar cell. So what is tandem? Tandem solar cell is basically the different layers of solar cells are put together to make a single solar cell. So let's say some solar cell are, the band gap of this solar cell is such that it is suitable for obtaining the absorbing higher energy photons, and the lower one, so it is not only absorbing high energy photons efficiently, but it cannot absorb the lower energy photons. So we are sandwiching our layer of different solar cell which can be utilized to absorb the lower energy photons. So we can put these two solar cells together. So the upper part will be absorbing the high energy photons and lower part will be absorbing the lower energy photons. So that is, so by that we can, from higher to lower energy photons, we can absorb the whole spectrum. So this is the structure, one PN junction here, one PN junction here. So this is also the explaining the same region. Since the high energy radiation which will be absorbed at this region, so it will not penetrate, so it will be absorbed here. But the low energy radiation, it can, since the penetration lengths are higher for this, so it can penetrate more, so it can be absorbed here at the lower region. So here we are leaving the lower energetic radiation, where here we are leaving the higher energetic radiation, so we can club them together, so whole region is utilized in that case. So this is the type of tandem cell. So these are giving efficiencies more than QS limit. So that is why we were defining the QS limit for the single channel, single PN junction. Or so if you club them together, the whole efficiency of whole cell will be higher. So the statement says the tandem solar cell improve the solar cell efficiency by using material with different band gap values. So your upper one will have different band gap value, this one, and the lower one will have different band gap value. Basically, the type of the material used there are different. So this is peroxide TiO2, this is silicon based. So this question is done. So it was already done. So I guess I have repeated all the questions.
Yes, sir.
Okay. So we still have some time to discuss and interaction. So if you have any discussion regarding today's lectures, you can ask. So we have so far done the PN junction part, the solar cell, their characteristics, their uses, and the solar cell construction. So our discussion for week 6 is done here. So if you have any doubts, any queries, you can ask. Otherwise, if you like, you may leave. I will be here till 9. So any questions there, I will be happy to answer. So again, I'm just reminding you, if you have not marked your attendance, you can mark your attendance by just writing your name in chat box. These are my LinkedIn profile and email addresses. If you have any doubts, you can mail me here, and I would be happy if you connect me there through LinkedIn. So you can connect me here. You can just directly search my name, or you can use this address. These slides are available on to you through the Google Drives, and as well as these videos are regularly updated on YouTube. The channel links are provided to you. So if you like to repeat or if you like to share with someone, so these are available there. So again, thank you everyone for attending today's session.
Thank you, sir.
Yes.
नाइन्थ नंबर क्वेश्चन सर मिसिंग था ना इसमें?
Ninth question, I guess, yes, it was
Yes,
missing.
yes.
सर ये जो क्वेश्चन था 9th नंबर में
Mhm.
वो है इफ द रिफ्रैक्टिव इंडेक्स ऑफ ए ग्लास एंड एयर इज 1.5 एंड 1 respectively, then what should be the ideal refractive index of anti-reflective coating material?
Okay, so I guess this was in the uh,
Mm, its option is given 1.425 and 1.335, 1.225.
okay, so that we need to calculate actually. So this relation you can use. Okay,
Okay, sir. Okay.
so this is the for the anti-reflective coating.
Mm-hmm.
So if you have N naught is for air, this is one, and NS for glass.
1.5.
So just
Oh, okay, that is
just
glass given 1.5 and 1 respect. So maybe the answer is option also given C number 1.225. That will be
2 to 5.
correct.
So that is also here. The 1.5 is for
Yes, sir.
glass and air one. So your
Yes, yes, sir.
film will be 1.225.
Thank you, sir. Thank you so much, sir.
So somehow I just skipped that question, but it is covered now.
Thank you, sir. Thank you so much, sir.
Okay.
Sir, am I audible, sir?
Yes, yes, you are.
Yeah, sir. One query, sir.
Hmm.
If photon energy is greater than energy band gap, then in this case, material is
Yes.
not visible. But if photon energy is less than band gap, then material will visible. Am I right?
For energy less than the band gap, it will be absorbed. Yes. For if your energy band gap is high, lower, and your incident energy or photo energy, your photo electron energy is higher, it will just pass it, then it will be transparent. Okay. So I had the relation somewhere. Yes. So your Eg should be greater than your E. E is your photoelectron. So this is the case for absorbing the light. But if your E, your photoelectron energy is higher, then it will not be absorbed. Then it will just pass it. Pass means it will be transparent.
Conduction band
Yes.
means if photon energy is higher than energy band gap, in that case, electron holes will pass from valence band to conduction band.
So it should be, for that it should be equivalent. For valence band to electron band, it will be equivalent, just to surpass the electrons from valence band to conduction band. For being visibly optical, it should be either lower, optically visible, it should be either lower or equal. If your energy is very high, then it will not interact, it will just pass through it. And if it is lower, let's say your Eg is higher and your E is lower, it is lower than this band gap, then the electron will absorb the energy, but it will not go to valence band to conduction band because it doesn't have the enough energy. So it should be at least equal to this band gap energy. That then only it will jump from valence band to conduction band.
Okay, sir. Thank you, sir.
Okay. Okay, so we are concluding today's session. Thank you everyone for joining, and we'll meet next week on Tuesday at the same time, 7 p.m. Thank you.